Welcome back to another tutorial on business analytics using Excel QM. Today, I'm going to talk about one of the most important topic in the probability named as Bayes theorem. Bayes theorem, named after Thomas Bayes, given a mathematical rule for inverting conditional probabilities, allowing the probability of a cause to be found given its effect. So in another word, we are going to calculate some conditional probability using the inverse probability and some prior probability knowledge. They also call it as updating your belief using new information as likelihood and your prior belief as the priority of the event. Before going into the detailed mathematical model and the concept, let's review the probability concept first. Probability of any event is a number between 0 and 1. It's 0 if that event never happened. It's 1 if the event happens all the time. And second rule of the probability is that the sum of the simple probabilities for all possible outcomes of an activity must equal to 1. When two events don't share any outcome, we call it two events are mutually exclusive. Events are said to be collectively exhausted if the list of outcome includes every possible outcome and they form the whole sample space. And if the events are collectively exhaustive and at the same time they are mutually exclusive, not sharing any outcome, we call it both mutually exclusive and collectively exhaustive. Let's go over some of the simple rules in probability. Complement, the set of outcomes that are not in one event. If this is a sample space which includes all possible outcomes, this shaded area is the possible outcome in event A, and the white area is the complement of A, where A is not happening. Probability of complement of A is equal to probability of A prime, or they call it also A complement, equals to 1 minus probability of A. For example, probability that a 7 is drawn from a deck of cards is 4 out of 52, or 1 over 13, because we have 7 cards out of 52 cards. So the probability that 7 is not drawn is 1 minus 1 over 13, which means that we can draw any card except from these 4 cards. Intersection, the set of all outcomes that are common to both events, sometimes called also joint probability. Let's assume that event A is shown by the red circle and event B is shown by blue circle. The shared area when both A and B happens is here in the purple area, and this is called A and B. The joint probability is shown by this formula, probability of A and B, or this one, or P of AB. From the previous example, the probability that 7 drawn and that 7 is also hard is only this card, so it should be 1 out of 52. That's called a joint probability for 7 and being a hard card. Union, the set of all outcomes that are contained in either of the two events. So we basically consider both A and B. We call it probability of A or B, and we show it as P of A or B. For example, either a 7 or a heart is drawn. So if a 7 is drawn, is this 4 item, or the heart are this 13. But we are double counting 7 here, so it is 13 plus 1, 2, and 3. 13 plus 3 is 16 out of 52 cards. Additive rule. For the union of two events, we can say that probability of A or B is the summation of probability of A and probability of B. Since we are double counting this shared area, we need to subtract one of those double count. So probability of A or B is equal to probability of A plus probability of B minus probability A and B. For the same example, probability that 7 happens is 4 out of 52, these 4 cards, plus probability that heart card is drawn is 13 card out of 52. Since we are double counting this 7, we need to subtract one of those double counting. So minus 1 over 52 equals to 16 over 52. Conditional probability. Probability that an event occurs given another event has already happened. We usually use this bar-shaped line here to specify the conditional probability, and we read it as follow: probability of A given that B has happened already. So B plays the condition role, and we are basically looking at the probability of A under that condition. That's equal to the joint probability divided by the condition probability. Probability of A and B divided by probability of B. From this function, we can calculate the joint probability, which is equal to probability of A given B multiplied by the probability of B. For the same example, the probability of a 7 given that heart has been drawn. This given that heart has been drawn is the condition, and we are basically looking at the probability of having 7 out of all the heart cards. So probability of getting a heart and 7 is only one card, 1 out of 52, divided by probability of condition getting heart cards, which is 13 cards out of 52. So if we calculate that, that would be 1 out of 13. There is only one 7 heart card out of 13 heart card. Independent. This happens when one event has no effect on the other event. So if the condition or event B doesn't have any impact on A, then the probability of A given B is simply equal as probability of A. So no matter B happens or not, this probability is always like as probability of A. So we can summarize the joint probability as the multiplication of the probability of two events. We call this multiplication rule. So let's assume we have two decks of cards, and A is drawing 7 from the first set of cards, and B is the event that 7 is drawn from the second deck of cards. So we are looking at getting 7 from both deck of cards. Getting 7 from the first card, the probability is 4 out of 52, and from the second card is also 4 out of 52. Now we can calculate the joint probability by using the multiplication rule, assuming that getting 7 or drawing a 7 card from two sets of cards are independent from each other. So that would allow us to calculate the joint probability simply by multiplying the independent probability. Now let's look at the Bayes theorem, which is basically based on the conditional probability and multiplication rule. I'm going to use the gift box example here in order to explain the Bayes theorem better. Let's assume that it's a Christmas and you got a gift, but you don't know what is in that box. You have the clue that you were supposed to get a pet, and there is a chance that the pet in the box is either dog or cat. So there is a 50% chance that the pet in the box is cat, and there is 50% chance that the pet in the box is dog. So somebody from the guests give you some information. The pet is very quiet. Now you have some new knowledge that you can update your belief or your guess, right? So statistically speaking, 80% of the cats are quiet and 30% of the dogs are quiet. So we have some conditional probability or the likelihood that help us to update our belief. Probability of a pet being quiet, knowing that it's cat, is 80%, and probability that a pet is quiet, knowing that it's dog, is 30%. So can you now guess what is in the box? Most of you probably guess it's a cat. But again, you're not 100% sure because still there is a chance that the gift, the pet, is a quiet dog, right? But you can talk about the probabilities. So let's assume that we have 60 pets, 30 of them are cat, 30 of them are dog. 80% of the cats are quiet, so we can say that around 24 cats here out of 30 are quiet, and 30% of the dogs are quiet, around nine dogs here from this population. We are looking for the probability of the pet in the box being cat, knowing that it's quiet, and the probability that it's dog, knowing that it's quiet. According to the conditional probability, we can write this function as the joint probability divided by the probability of the condition. So probability that we have a cat, knowing that it's quiet, equals to probability that it's quiet and cat, or cat and quiet, divided by probability of being quiet. Same thing for dog. Probability of getting a dog, knowing that it's quiet, equals to probability of being a dog and quiet, divided by probability of quiet. Now we have the probability of quiet and cat, that's 80% of the population of the cats, and this is the 30% of the population of the dogs. We need to find the probability of being a quiet pet. Let's assume that we only have the cats and dogs. The probability of quiet can be calculated by incorporating whether it's a cat and quiet or dog and quiet. So we can say 24 plus 9 out of the whole population of 60 pets are quiet. So mathematically speaking, probability of being a quiet pet is probability of being cat and quiet plus probability of being dog and quiet. That's 80% of cat and 30% of dogs. So now we can rewrite it based on the multiplication rule. Probability of being quiet and cat is probability of being quiet given that it's a cat, multiplied by the probability that it's a cat. That is 50% of the time. Plus probability of being quiet and given that it's dog, multiply by the probability that it's dog, which is 50% of the time. That's our initial belief. So now we can calculate the probability of being cat given that it's quiet by using the multiplication rule and expanding this joint probability. Similarly, we can expand the probability of quiet as we discussed from the previous slide. Now, probability of getting a cat. Now, probability of having a cat in that box, knowing that it's quiet, it's equal to probability of a pet being quiet, given that it's a cat, multiplied by the chance that you are getting a cat, divided by probability of being a quiet pet, knowing that it's cat, multiplied by the probability of getting cat, plus probability of being a quiet pet, given that it's dog, multiplied by the probability of being dog. Same thing can be written for the dog. The chance that you are getting a dog, given that it's quiet, it's equal to this equation using a multiplication rule and conditional probability. So basically, we are looking at an inverse conditional probability using the original conditional probability. So if we use the numbers, we can calculate this probability. Probability of a quiet cat or a quiet pet, given that its cat, is 80%, according to the statistic or the new knowledge we have, multiply by 50% chance that it's gonna be cat or dog, divided by the same thing, 80% of the cats and 30% of the dog chance. That results in 72.7%. Same thing for the dog. We have the probability of quiet pet, given that it's dog, multiplied by the probability of dog, 30% of the dog, divided by the total probability of being quiet. Either it's a cat, 80% of cat, or it's a dog, 30% of the dog. So in summary, we have prior probabilities. There is 50% chance that it's a dog in the box and 50% chance that it's cat. Then we get a new information that the pet is quiet. Then we use that information to update our belief and calculate the posterior probability. So instead of 50% chance, now we have 27% chance. So still, the chance that it's cat is higher than dog. Let's review the mathematical formulation again and go through the mathematical proof of that equation. We know that for the conditional probability, we have this function, probability of A, given that B is happening, is the joint probability divided by the condition. Same thing, probability of B happening, given that A happens, equals to joint probability divided by the probability of A, or the probability of condition. From this function, we can calculate the joint probability as follows using the multiplication rule. We also know that probability of B and A is same as probability of A and B. So we can insert this probability back into the first conditional probability and come up with this Bayes' theorem function. Probability of A happening, given that B has happened, is equal to probability of B happening, given that A has happened, multiply by the probability of A divided by probability of B. This is the core function for the Bayes' theorem. We are using a prior probability and initial likelihood to calculate the inverse conditional probability. This is the same thing we did in our gift box example. We also can expand probability of B, which is the condition here, by considering different conditions that we have. So here in our example, we have only cat or dog. And probability of the condition, or being quiet pet, was probability of being quiet and cat plus the probability of quiet and dog. Notice that if we have another condition like being a rabbit in the box, then we need to add it to the condition probability. So we need to add the probability of being quiet and the rabbit. But for now, let's forget about that and let's stick to two conditions that we have. Either it's a cat or dog. So we can expand the probability of condition by using the multiplication rule. Either it's quiet and cat, or it's quiet and dog. So we can substitute this expanded formulation in the Bayes' theorem, the core function, and we can get the expanded Bayes' theorem, where A prime is the complement of event A. So A is being a cat and A prime is being a dog. Only two different categories here. Now let's solve another example to understand this better. A cup contains two dice identical in appearance, but one of them is fair and the other is loaded. The probability of rolling a 3 on the fair die is 1/6. The probability of rolling a 3 on the loaded die is 60% or 0.6. We select one of the die by chance, we toss it and get a 3. What is the probability that the die rolled was fair? So we are looking at finding this conditional probability. What is the probability of being fair, knowing that we already got the 3 when we tossed the die? First step is summarizing the data that we have. There is 50% chance that we select fair die and 50% chance that we select loaded die. The probability of getting 3 on the fair die is 1 over 6, and the probability of getting 3 on loaded die is 60%. We can use multiplication rule to calculate the joint probability. The probability of getting 3 and using the fair die is probability of 3, given that it's fair, multiplied by the probability of being a fair die or selecting a fair die. So that would equal to 0.166, probability of 3, given that the die is fair, multiplied by the 50% chance that we select fair die. Probability of 3 and selecting loaded die is probability of 3 given that the die is loaded, multiplied by the probability of selecting a loaded die. That's 60% multiplied by 50%. Now we have two joint probability. We can calculate the probability of getting 3. So no matter it's fair or loaded, we want to know what is the probability of getting 3. Probability of getting 3 is equal to either we get a 3 unfair or get a 3 unloaded die. So it's equal to probability of 3 and selecting fair plus probability of getting 3 and selecting loaded die. That's equal to summation of these two numbers. 0.083 plus 0.3 equals to 0.383. Now we can use the Bayes theorem to calculate the probability of selecting a fair die knowing that we rolled 3. That's equal to probability of getting 3 knowing that it's fair multiplied by the probability of fair divided by the probability of getting 3 no matter it's fair or loaded. So we just need to substitute the numbers and get the result. There is 22% chance that we selected the fair die given that we rolled 3. And that does make sense because the probability of getting 3 on the loaded die is higher than the probability of getting 3 on the fair die. So basically, the probability of selecting a loaded die when we have the 3 is higher than selecting a fair die. So there is 22% chance we have selected fair die, and there is 78% chance that we selected loaded die. Well, I hope these examples helped you to understand the Bayes theorem better. In summary, Bayes theorem is useful in updating our belief, and it has a lot of application in AI and machine learning, in medical science, especially with those false positive and true positive, false negative test result. So we use some prior knowledge, we get some new information or likelihood, and we update our belief under some conditions. In another definition, you use conditional probability to find a reverse conditional probability. That's a core concept for Bayes theorem.